from Cleveland, and since 1976, USS Cod SS-224 has been docked in Cleveland, and it was a wartime Gato-class submarine. They had multiple patrols. The thing's been depth charged. It's been shot up. There's bullet holes in it. Dished in deck plates topside. It's a heck of a tour, and I recommend that you come up to Cleveland, and if you're ever there, come see this thing. However, every video that I've ever seen about it tells you what it is, but doesn't tell you how it works. So we're going to try to do a video here where I'm going to maybe explain some of how this thing, how do you turn diesel fuel into 1,500 tons that go that way. And please note that during this description, I've never done it. So the experience of how to operate it is different than knowledge of how it operates. I'm not talking about how to run this ship. I don't know how to run it. I don't think there are many people left alive on the planet that have ever driven one of these things. However, I'm going to take a stab at this and see if I can do some sort of a job of explaining what's going on back in maneuvering. There's a lot of energy stored inside this thing. It is a weapon, and you got to remember that. A lot of men gave their lives for something they believed in this exact kind of ship, and they should be remembered, and remembered with that amount of respect. Anyway, having said that, let me take a crack at this. Here we have a cross-sectional view of a Gato-class submarine. Hidden in this thing are two very heavy batteries. The ship weighs 1,500 tons. These batteries are about 350 tons of it. It's a significant percentage of the ship's overall displacement is just keeping these batteries afloat. They're big, they're heavy, and they're totally inadequate for going underwater, but it's what we had back in the 1930s, 1940s. Also inside of this 1,500 ship are 1, 2, 3, 4 railroad locomotives, and underneath number 3 and number 4, another half of a railroad locomotive called an auxiliary generator. Behind that is the motor room, where we have 4 750 horsepower electric motors, geared 2 apiece, each to a gearbox, and out the back end of the ship to the screws. Above that motor room is where the magic happens. That's the control cubicle. We're going to talk about when you move the controls in the control cubicle, how do you make the motors push the ship, and are you turning the motors with the batteries or the diesels? Above the motor rooms and behind the 4 railroad locomotive diesel engines, there is a device called a control cubicle. It's pretty big. It's about 12 feet long. It's around 7 or 8 feet tall. It's about 3/4 of the diameter of the hull around. And inside this box are all of the circuit breakers, switches, contactors, and interlocking devices necessary to allow us to operate the motors with the engines or with the battery or do a battery charge. It all happens in this one cubicle. Behind the back side of this cubicle, there are a group of fairly ergonomic levers that stick up that allow you to do certain things. We're going to manipulate these levers and watch what it does on a circuit diagram. Let's go. We're at all stop in calm water. We've got the number 1 diesel running at full cry. It's up on its governor and ready to take load. Let's move the ship. The direction levers are pushed forward. That sets up the stack on top of the motors to take forward directional motion. Current will flow through the armatures in a direction that causes the shafts to spin and have the screws push the ship forward. The next thing we are going to do is we're going to shut the starboard and port motor bus tie breaker by moving the center lever to the bus tie closed position. This will shut 3-3 and 3-4. With the bus tie shut and the 2 motor buses tied together, we'll then close in switch number 5 and 7, the number 1 generator. The number 1 generator cannot be put on the bus unless it is up to voltage It has its field amps confirmed by several interlocks, and the engine man up in the engine space has allowed maneuvering to have it. When we now pull the starter levers back to position 1, contacts number 39 and 43 will shut. That will cause current to flow through the motors, 2 in series, 2 sets of series motors in parallel. We are now moving forward. The starting resistors can hold this current for about a minute, and they're holding the inrush through because as the motors are not turning, they are essentially short circuits. So we have to create a place. We're making an enormous amount of heat while we're doing this, so we don't want to dilly-dally. The sticks come back to position 2, and when at position 2, contact 4-1 and 3-6 shuts, and they shunt out one of the resistors. Then we go back to position 3, which is our steady state running condition. Contacts number 40 and 45 shut, and now both sets of starting resistors are shunted out. We're running 2 in series and 2 sets in series in parallel. So each motor is seen at 135 volts. We can add an engine to this. So let's add number 2. We're going to close 9 and 11 and open 3-3 and 3-4. This will split the propulsion plant so that the 2 engines you have running are in one engine room, and the propulsion plant is split. So a casualty on one side has less of a chance of affecting the casualty on the other, and you don't come to all stop. Stopping a submarine in a war zone is bad. Don't do that. Let's transition to submerged operation. Think of the batteries as a bank account. We're gonna make a withdrawal from the energy that we've stored in the batteries. The first step is going to be to go to both on the battery selector switch. That will close 1, 2, 3, and 4. Ignore 1 alpha through 4 alpha. Those are manual disconnects down on the battery wells. They're always closed. Don't worry about it. The next thing we'll do is we're going to hook the battery bus to the motor bus, and we will close contacts 29, 30, 31, and 32. So now the engines and the battery are running in parallel for a very short period of time here. I'm assuming that they ran the engines at the open circuit voltage of the battery to make this transition quicker. You open 9, 11, 5, and 7, drop the 2 generators off, and now we're doing the same bell we were doing on the engines on the batteries. I'm going to assume that control is going to taper that off a little bit, because if we were doing a decent bell on those 2 engines, those batteries do not have the same oomph. They will deliver a lot of amps, but they won't deliver it for a long period of time. So if we're doing 10 knots on the surface and we submerge in this alignment right here, and now we're running on the batteries, we got a half an hour. So I'll guarantee you they're going to be dropping this bell off pretty quick. But here we sit, and now we're on the batteries for propulsion. And we can sit here for a little while, anywhere between a half an hour, and I think they could stretch this out over a day. But again, I will say the batteries are a bank account, and we make deposits with diesel fuel, and we make withdrawals with heat and propulsion underwater with no air. We'll surface again, and when we get up on the surface, we're still moving the ship with the battery. The engine men have signaled that number 1 and number 2 are ready to go again. We're going to put those back on the bus, here and here. So now we have the 2 engines driving the motors. We'll separate the battery bus from the motor bus, and we'll fire up engine number 3 and get ready to do a battery charge. By shutting 1-4 and 1-6, and then we'll do a battery charge with engine number 3. By managing engine number 3's output voltage, we can control the amount of current flowing back into the battery. While we're doing a battery charge, we're measuring several things. One is amps going in, and you might need 2 engines to do a battery charge. If you went really deep, you might not. This is a very flexible system. While you're doing a battery charge and while you're doing a discharge, you got a couple of guys on individual cell voltage panels looking at each and every cell. For low cells, you're looking for anything that's out of place. But the big one's going to be, you don't want to take a battery cell down so low that it starts charging up the wrong way. Also bad. So that's what the individual cell voltage panels are, located up in officer's country, and then there's one an after battery in a locker that's outboard. Everybody's crawling on top of everybody in this thing. Not the most comfortable piece of kit in the world. But when you put 40 or 50 guys in a 1,500-ton boat, I don't know where you were expecting them to sit. This is a chart that we truncated off the side of the main drawing here. In this chart, it tells you exactly which contacts are closed and which ones are not closed while you're running. So if you want to see how to run this thing in parallel, run it in slow, run it in anything, move the levers over on the chart and then take your colored pencils, which every good nuke has, and start coloring stuff in, and it'll really help you understand this. It took a phenomenal amount of time to animate this, and I'm not going to go through the rest of them, but just move the levers where you want it, color in the dots you want, and bang, here you go. Auxiliary power, shore power, DC shore power, appears to connect to the battery bus on the left side. Where the auxiliary generator ties into all this, there's this completely separate distribution system for lights, blowers, fans. There's a lot of stuff going on here. The electricians on this ship were really busy. Here's a couple of photographs I took down in the motor room. It's really tight down here. They got 4 motors crammed into this thing, 2 gearboxes, 2 thrust bearings. And here's a picture of the hull penetration where the starboard shaft goes out through the hull. And you've got a shaft packing on that. You can tighten up that gland with those studs sticking out. Really, really tight. In this photograph, you can see that there's 6 inches in between the number 2 and number 3 motor. You're not going to get in between that. And that space that you're seeing forward of those motors has the control cubicle parked right over the top of it. I get a feeling these guys did not do a lot of preventative maintenance while underway. I think all that got done in port when you could turn off all of the power in the control cubicle and move around in it and not get shazammed up there. There's just not an enormous amount of room in this boat. So down here in this motor room, you have basically four lube oil systems that take care of the 4 motors, the 2 lube oil systems that take care of the 2 gearboxes. You can see temperature probes all over the place, and all of this stuff reads out on the back wall of maneuvering. You're keeping track of oil pressures, you're keeping track of temperatures, you're keeping track of air moving through the battery, you're keeping track of hydrogen being given off by the battery, you're keeping track of a lot of stuff. We did not animate the meters because you couldn't see it on a screen, but here's a shot of the port and starboard meter banks that are showing you kW coming out of the engines, field amperages, and everything else. Now, last thing I want to talk about. You'll see that the volts adjust pots on the diesels rotate in the opposite direction that the voltmeters move. It's counterintuitive until you look at the fact that charging amps on this meter here increase in a counterclockwise direction. So if you increase the generator voltage, you will increase the amount of amps going into the battery during a charge. Of interest is the meter above it, and notice that after battery DC thousands of amps, kiloamps, you can charge, the meter only goes to 3,000, but on discharge it goes to 9,000. This thing is the gift that keeps on giving. Anyway, ergonomics matter when you got a bunch of 20-year-old kids that are getting depth charged and shot at, and they're tired and they haven't had any sleep for a month. It starts to matter. So little things like your critical direction for turning the pot matters here. In this video, I've attempted to show you where the current goes. Some of the things that are there's a lot of underlying theory that's missing out of this because there's no way I can describe it. Motor theory, battery theory, but we're trying to show you how to read this diagram and create your own scenarios if you really want to know what's going on and where. Do not underestimate the magnitude of the amount of electricity and the amount of power that's inside a very small space. These guys really had their act together to manipulate all of this and not blow themselves up. And I mean that literally. Not to mention the fact that, well, you had, torpedoes in there. There were a lot of things in this ship that'll kill you. There's only 2 things that belong in the people tank: people and air. And just remember, there are only two kinds of ships in the Navy: submarines and targets. As always, it's been a pleasure.